Every single year, over 1.3 million people die in car crashes worldwide. But here's the number that almost nobody talks about. A significant chunk of those deaths happen because of something your car does at 60 miles per hour that you've probably never thought about in your life. Your tires start floating. Not metaphorically, literally floating, on a thin layer of water, with zero grip and zero warning. And the only thing standing between you and that moment? A few tiny grooves carved into the road. After this video, you will never look at road pavement the same way again. Let's put this in perspective. Right now, at this exact moment, there are approximately 1.4 billion cars on the roads of planet Earth. Each one of those cars, at highway speed, is resting on 4 contact patches of rubber that are roughly the size of a human hand. 4 hand-sized patches. That's it. That's all that connects a 2-ton machine moving at 100 kilometers per hour to the ground. Now pour rain on top of that, and suddenly you have a problem that engineers have been quietly obsessed with for over a century. Because when water gets between a tire and a road, something terrifying happens, and it happens fast. But here's the interesting part. Humans didn't actually understand this problem until people started dying at high speeds. Back in the early 1900s, roads were just packed dirt and gravel. Cars were slow, rain was annoying but not lethal. Then came asphalt. Smooth, beautiful, fast asphalt. And almost immediately, something weird started happening. Drivers would report that in heavy rain, their cars would just slide. Not skid, slide, like the steering wheel had been disconnected from reality. Nobody could explain it. It wasn't until the 1950s and 60s when jet aircraft started skidding off runways on wet tarmac that engineers at NASA and the US military finally gave this phenomenon a name: hydroplaning. And the moment they understood it, they realized roads and runways had to be completely redesigned. What they figured out would quietly save millions of lives over the next 60 years. Okay, here's the physics, and I promise it's simpler than it sounds. It comes down to 3 things. 1, speed. The faster you go, the less time water has to get under your tire. 2, water depth. Even a thin film, we're talking millimeters, is enough to cause a problem at the right speed. 3, drainage. If water has somewhere to go, it goes there. If it doesn't, it goes under your tire. That's the whole game. The tire needs to push water away from the contact patch faster than the car is moving forward. And on a perfectly smooth surface, it simply cannot do that above a certain speed. This is where it gets crazy. Picture this. You're driving at 90 kilometers per hour. It's raining. The road ahead looks totally normal. But at the front edge of your tire, there is a wall of water building up, like a bow wave on a boat. And your tire needs to split that water, push it sideways, and maintain contact with the road surface, all in a fraction of a millisecond. On a smooth road, there's no path for that water to escape. It has nowhere to go, so it does the only thing it can. It lifts the tire. Just slightly at first, then more. And the faster you go, the worse it gets. At around 90 to 100 kilometers per hour on a wet, smooth surface, a tire can completely lose contact with the road. You're not driving anymore. You're gliding on water. Your brakes do nothing. Your steering does nothing. You are now a passenger. But here's where those tiny grooves come in. Road engineers call them texture, and they're not random. Every groove, every ridge, every rough patch on a road surface is precisely engineered to solve exactly this problem. Think of it like a drainage system, but invisible. Those tiny grooves create microchannels. When your tire rolls over the surface, those channels act like tiny rivers, giving the water a path to escape sideways, away from the contact patch. It's the same reason your tire has tread patterns. The road and the tire are working together as a system. One drains from the bottom, the other drains from the top. And when they work together, a tire moving at 100 kilometers per hour can displace roughly 8 liters of water per second. 8 liters every second per tire. That's like emptying a large water bottle every single second from a contact patch the size of your hand. But here's something most people have never heard of. Modern roads aren't just textured, they're directional. In many countries, highway surfaces are engineered so the grooves run at a slight angle, not straight across, but diagonal. This creates a centrifugal effect that actively throws water toward the edge of the road. On top of that, roads have a hidden slope called camber, usually between 1 and 3%, specifically designed so that the entire road surface functions as a gentle ramp, constantly pushing water toward the drain channels on the sides. So the next time it rains and you see water flowing off the road to the sides, that's not an accident. That's engineering. The road is actively working to save your life, and you've driven over it 1,000 times without ever noticing. And here's another layer to this. Not all road textures are the same, and this is where it gets genuinely fascinating. Engineers actually use different textures for different situations. Highways use a pattern called longitudinal grooving, long channels running in the direction of travel. This is optimized for high-speed drainage. Curves and intersections use transverse grooving, channels running across the road. This maximizes grip when you're turning or braking. Airport runways use the most aggressive texture of all, deep, precisely spaced grooves that can handle a 300-ton aircraft landing at 280 kilometers per hour in a tropical downpour. Every single environment gets a custom surface, designed, tested, engineered. And here's the detail that really gets me. Road surface engineers test their designs not just by how much water they drain, but by how much noise they make under a rolling tire. Because believe it or not, road texture is one of the biggest sources of traffic noise in cities. So engineers are simultaneously optimizing for grip, drainage, noise, durability, and cost, all at the same time. So what does this actually look like in practice? When road crews build a new highway, the process doesn't end when they lay the asphalt. After the surface is poured and cooled, machines called texture rakes or diamond grinders come through and cut the exact groove pattern into the road. The depth and spacing of the grooves is specified down to the millimeter based on the expected speed limit, rainfall data, and traffic volume of that specific road. And those roads get tested. Vehicles equipped with sensors measure something called the skid resistance number, essentially a score for how well a surface stops a car under wet conditions. Roads below a certain score, they get resurfaced before anyone dies. And one of the wildest parts of this whole system, roads degrade over time, not just from cracking and potholes, but from polishing. The millions of tires rolling over the surface slowly smooth out the microtexture, like sandpaper wearing down. And as the texture disappears, wet weather grip drops with it. So that's why road maintenance isn't just about fixing potholes. It's about preserving the microscopic surface structure that keeps cars on the road. One more thing most people never realize. The color of old roads, that shiny, almost black look of asphalt, that shine is a warning sign. A new road surface is matte and rough. As it wears down, it becomes reflective. And that reflection, especially visible under streetlights in the rain, is telling you that the microtexture is gone. That beautiful wet shine on an old road, that's the road telling you it can no longer protect you. Here's what I find remarkable about all of this. Roads look like one of the simplest things humans make. You pour some material, flatten it, done. But underneath that apparent simplicity is a system of extraordinary precision, engineered to manage water, speed, weight, friction, and noise, all simultaneously, invisibly, every second of every drive. Those tiny grooves aren't decoration. They're not wear marks. They are the result of decades of physics, disaster, research, and refinement. Every time it rains and your car holds its line, quietly, confidently, without drama, something remarkable just happened. You just drove over thousands of miniature drainage channels, each one placed with intention, doing their job in a fraction of a millisecond. And they worked. They always work. Until the day the road gets too smooth and nobody noticed. Now, if you think road surfaces are a hidden engineering marvel, wait until you hear about the material underneath them, because there's an entire invisible world of layers beneath every road you've ever driven on. And the deepest one was designed to survive something no car could ever produce on its own. We'll get into that next.